Good morning once again to all. I welcome you all to the data science program by IIT Guwahati. In the previous sessions, we were discussing about the convolutional neural network under the module of computer vision. So let's have a quick recap of what we had discussed. And today's session will be mostly related to that. And we are going to extend the concept what we had discussed in the previous class. Okay, so the first topic we discussed in the previous class was a multi-layer neural network, and we first discussed about a specific method of updating the weights by using what is called as a EBP technique, or it is the error back propagation. Right. So normally, whenever we have a hidden layer present in our neural network, right, we cannot apply the delta learning rule, which is capable of the simple binary classification under the linearly separable data set, right? So that's what we had discussed before the previous session, and now uh, in EBP we understood that, right? So first step will be the forward propagation, give some inputs and calculate the we calculate the output. That's a forward propagation. And we also have understood that we can use the matrix representation, right, for the easier calculation, and right, and for the programming purpose. That's going to be very helpful, right? So these are the equations, right, which we had used. Then, in order to update the weights, we can apply the delta rule for only the output part, right? Because these are the delta values which we can directly calculate, right, by subtracting the current output y from the desired values d, right? So that gives delta values corresponding to the output, so which are directly implemented in the delta learning rule. But right, we can understand that there are many other weights which are connected to the hidden layers or the layers before, right? So that means I have to find out a technique to update those weights. So our approach will be calculating a delta of the previous, right, layers as well. So in order to calculate those delta, we need the errors like, so somehow if we are able to calculate the errors over here, I can convert the errors into the delta values and we can. So like this keeps on propagating until we reach the input level. So that was a fundamental idea. And we could achieve that by using what's called as the error back propagation. We could calculate the errors of each of the previous stages, right, and we could convert them into the corresponding delta. So once we have a delta, right, we can consider this as the output node of this part of the circuit, this part of the neural network, and right, we can update those weights by using the simple delta rules again. So this was our fundamental idea, and we could extend this, and right, we could perform the calculations, right? So we had a few examples over there, and also we had written some basic codes to implement that. Okay, at a later stage, definitely we are going to write the uh, practical examples implementing using the standard libraries like TensorFlow, Keras, okay, etc. We will come to. So far, do you have any doubts in, or anything you want to discuss? So let's discuss, and let's proceed further. Any doubt you have, please feel free to ask. Okay, all right. So that takes us to the next step, right? Which brings us more closer to the requirement of the conversion of the neural network into the deep neural network. And in the deep neural network, we face some problems, which results in moving ahead to the concepts under deep learning, which starts with the convolutional. Okay, so that's the flow. So we started from the neural network, right? We move ahead. Now, so far we understood that the weight updation happens, right, following the error back to propagation. But the fundamental idea here is that I may use any of the weight updating schemes, right? If you recall, we had discussed about three different weight updating schemes. The first one is pretty straightforward and the simple one, that is the stochastic gradient descent. Every time you give a data as input, right, it learns something, right? And you decide whether the weight updation is required or not, right? So that was option, right? If there is error, update the weights, otherwise don't update. You can use any of the weight updation algorithm over. So every time you update, it's a stochastic. Then you can actually convert the whole data set into a batch, right? And take up an average of the every time delta values we get, and we can definitely decide to have a weight updation agreement. So why that particular technique is significant? It actually reduces the computational load, right? Of a very large network, when I have hundreds of hidden layers, you don't have to update every time, right? But definitely, yes, right? We can wait for some time so that, right, computation load to the machine that actually reduces. Anyway, so there will be some effects of that, right? Maybe the machine may not give you the accuracy, right? Under the fixed number of iterations, if you compare SGD with a batch, right? We have done that already, so we could understand that. Yes, so these are the consequences. If we are ready to take that, and if we are ready to go for higher number of training data set, etc., yes, that is fine. So that's the concept, right? So irrespective of those methods, we have the weight getting updated. But one point we need to understand: current weight update is not going to consider any of the previous weight updates, because you see, maybe we start from a point, right? So let us say I'll try to draw something. Let's say this is the curve, right? So I want to reach this point, it's the minimum point, but the weight updation may happen initially. It's error. Okay, error is here, error shifts here, right? Because weight changed. Maybe weight changes in the negative direction further, so error further reduces. But after a sudden, because of the next data, right, your error may shoot up. So it may go here. Now you see that it's actually, right, my error, I want to reach the minimum point, which is here, but it's actually, right, moving here and there randomly because of the data set. Now, whenever we go for the training process, right, it's very crucial that we see to that our data set is very proper. In the sense, I have, say, cat and dog. When I say in the supervised learning technique, when I say I'm training this particular data set, I have, say, two folders, one folder containing 10,000 images of cats, another one containing 10,000 images of dogs. There should not be any misplacement. In a dog category, I should not place a cat, right? Even if I place it by mistake. So whatever you see on this particular screen, that graph, right, the error update, the weight update will not happen, because it tries to learn cat as a dog, which is wrong. So in such cases, what happens, right? It's not going to come in the same direction, because now I'm bringing the word called directionality, right? In the sense, my initial error is high. I want to make the error to come down, right? So it may be moving to the other side of the graph. That doesn't matter. All right. I want to keep reducing the error. Error should not boost up. So what if you try to bring a parameter, right, which controls this directionality, right? So I want to bring that, in the sense, to all the previous cases, right, error was decreasing. By mistake, I placed a cat inside the dog category, so that whenever it sees, okay, I'm learning a dog category, but it says it is a cat, right? So it learns, it thinks that there is an error, so error will boost up, error will go up. So the direction in which it was coming down, now it changes, right? So that's the whole idea behind, right, this concept, which is called as a momentum. So in order to bring another adjustment for our weight updation, we use a term called as momentum. All right. So weight adjustment, we want to give a direction for that. That's the whole idea, right? So previous cases, whatever is the weight corresponding, sorry, whatever is the input data, you get a weight. Corresponding to that, you get a error, right? If error is positive or negative, you have a delta W being calculated, right? And that delta W will be applied immediately for the weight updation algorithm. So del Wij is equal to Wij old value minus eta times something. So that something is what we call as delta W. It is positive or negative depending on that, directly we apply. Okay, so that was the idea so far, irrespective of which scheme we are going to use, right? So SGD, immediately you change delta W depending on that, plus minus 2. So if we go for the batch or mini batch, we'll wait for a certain time, but still you are going to apply that, right? As soon as that particular wait time is over. So once the data set is given, you update it. But we are never considering what was the change in the weight previous to this change, previous to this update, weight update. What was the case much before that? All of them were trying to bring it down, down, down. All of a sudden something goes up means, right? I should have a control. This is the idea. So rather than trying to produce an immediate effect, right? That's what you see. Immediate change. I don't want the weight to shoot in an opposite direction so that error increases all of a sudden, right? So I'll try to bring the effect of other weight updates previous to the current update. All right. So the word is called as momentum because it is very similar to the physical. In physics, we have the concept of momentum. So let's try to bring that, right? So now this is the notation which we are taking from the external forces, right? So anyway, momentum is nothing but, so past weights, let's say, plus a beta, which is a parameter, into the values of the past momentum. Past momentum plus the change in the weight we'll try to apply, right? So I'll come to that, right, as applicable to our concept. Now we see, right, we have in this set of equations, we have few terms defined. So one is m minus, which is the previous momentum, right? So how to start with, we'll see. All right. So let's say currently I'm trying to update. I have all the past values accumulated in a variable. That is what I'm going to call as m minus, and a constant, right? Again, you can have something similar to a learning rate, right? Which is called as a controller of the momentum. We call this as a beta in the notation, which is between, normally it is kept lesser than 1. Definitely not negative, more than 0 and less than. Right. So what we are trying to do here, initially, right, keep the momentum as 0, right? Because we have never trained anything so far. The first data, training data, is yet to be given. All right. Under such condition, we keep m of 0, 0 here. What 0 we are writing? It's an index in that. Okay. Which this is a counter for what's the training data that is going into the machine. All right. So m of 1 is equal to, so delta W, it's fine. Anyway, whichever method we are following, we get a delta W. Into, you see, beta times m of 0. Correct? So that beta of m of 0 will be the past momentum multiplied by a beta. So if at all there was a value here, that would have been taken care of, right? When with the delta W. But again, I see that in this case, this will be a 0, right? M of 0 is going to be 0. So I'm going to get only the delta W1. Right, so that's what is the term. Okay, so next I'll go for n of 2, the next momentum value. According to the equations we have shown here, right, you can see that this is delta W2, the expected value of the change in the weight. Can be positive, can be negative, right? Depending upon the error value, we can do that. Plus the beta times m of 1. So you see that beta of m of 1 is my previous momentum value, which actually takes care of its previous value, right? M of 0. But beta is a smaller number. It is not 1 normally. It is lesser than 1, right? 0.5, 0.75, all these values will work. All right. So, but you see, since I'm multiplying by a value lesser than 0.5, right? It's the weightage for the oldest momentum what I have keeps on reducing. So now I'm multiplying by 0.75. Next time it is actually 0.75 square into the previous. So its weightage keeps on reducing. Most recent values will be considered. That's again one of the method we can apply this concept in our own way to make the changes for sure. All right, so M of 2 equation is delta W2 beta times delta W1, which comes from the previous case. Right, similarly, now you can extend this further, get M of 3, delta W3 plus beta times M of 2. Beta is again a constant, M of 2 is my previous momentum. So that can be expanded like this. So you can see, right? So the momentum after training the third data set, it actually depends upon the present change in the weight plus beta times the previous weight, beta square times its previous weight update, whatever was the delta W. So you see, we are trying to bring a directionality to our weight update, right? So if assume one of them was, let us say the delta W2 was maybe negative, right? But delta W1 and if delta W3 are positive, right? Your weight update will not go in a in a wrong direction. It will come to the required direction. That's what is assumed, right? Unless and until we have a bigger delta W values in the wrong direction, this will do the job, right? So most of the time what we have observed is, right, yes, it's going to give you a proper direction for the weight update. So what are the points to remember? Now, older the weight, right, if you have very old weight gets lesser influence on the momentum, okay, because most recent data is that's what we are expecting to put more influence. They should influence more on the current update. That's what is the fundamental idea. That's why, right? So we multiply by a beta, which if we keep it lesser than one, its influence, right, it tries to reduce the influence of oldest, right? So as we already understood that, so it as the time progresses, right, in the sense the oldest one, you don't have and you may not see any effect, okay, right? But definitely we can see that they will be present in their effects will be over there, but they may not influence by a huge margin. Okay, so weight is not solely affected by a particular value. Current change is not the only one deciding that. All the accumulated values of the past weights will also come into picture. So because of the directionality, we can use one particular word called as a stability, right? It tries to stabilize the process of uh, weight operation. Okay, again, this momentum is an accumulation, so we can understand that, right? It's going to grow more and more as and when we have the weight updates, right, are going with huge number of data sets. So momentum grows more and more with the weight updates, right? So right, so this is the whole concept, right? We can definitely use the momentum. So in any of the codes, if at all you want to try with the basics like what we did in the previous cases, right, you can try to implement this as well. All right, you can try to bring the concept called as a momentum, and right, you can implement. So this is supported in many of the tools or the libraries which we are using, right? Anyway, when we write the codes using Keras, TensorFlow, PyTorch, etc., we can use, right, the concept of momentum as well. But right, just to before going for a coding, it is necessary that what exactly each of those terms specify. All right, so that's about the concept of momentum. I hope this is clear. Please let me know if you have any doubt. Okay, so let's move further. And the next concept is a cost function. So basically, we already have used the cost function. It is nothing but the error calculation. How do you calculate the error? So previously, right, in case of the delta learning rule, we use the straightforward calculation, right? That is nothing but error is equal to the desired value minus the output value, d minus y. Okay, so it's pretty straightforward. We get both positive and negative values for the cost. right? So error is more means you need to study more, right? So that's why we introduce the word as a cost function. There is a cost. You need to learn more for that, right? You make a bigger error, right? You need to study more, right? So you need to learn more when it comes to machine. So it's a cost because computational load is more training is required, right? It takes more time, right, etc. So we are going to put a lot of pressure, a lot of load on the hardware, right? So because of that reason, we will call the word as a cost function, but fundamentally we can understand that it's the error term which we are calculating. But uh, should we stick to only that simple equation, that is error is equal to d minus y? So we already have seen that if you are trying to calculate the error, right, if you're trying to plot the error in a different way for a plotting purpose, this error is not going to work. E is equal to, right, d minus y may not work. We already have seen that earlier, and we shifted to the absolute error, right? So we squared error, I guess, right? So we had used d minus y the whole square, and you accumulate. So that's one thing. So we can see here we have written two different functions, right? One is the first function. It's the standard notation for cost function is a j, though we use it as e in our function. Okay, so how much error a network produces whenever it is learning with a particular data point, we call it as an error. So if you have a greater error, right, you need to learn more. So we need to we need to have a higher cost for that. All right, so let's see, we have two functions. We will give the name for both of them, but first function is the one which we had used in one of the previous course. We took a sum of, right, the d minus y whole square. Maybe the 1 by 2 is not there, but the standard function what people use in the industries, there is a multiplication by a half, right? Even we can multiply by various numbers over here, but anyway, that's going to reduce your amplitude by certain factor, that's all. Okay, if we keep that factor constant for every method or every thing which I want to compare, it's going to have the same effect, right? So doesn't matter whether you have half or not. Similarly, we have another function which is, right, like this, right? We are going to look at both functions in more detail now. All right. So the first function is a sum of the squared error, SSE technique. It's called as SSE. You can even go for a mean, right? Mean squared error, root mean squared error, etc. Fine. So this function, I'll show you the graph and let's discuss with the graph. All right. So how the first equation is going to calculate? It's pretty simple. Take a difference, d minus y. If that may be a positive or negative, right? So if it is positive, we don't have any problem. If it is negative, when you take a sum, that reduces your total error, right? It says that error is lesser. So in order to avoid that, we square it so that even the negative numbers become a positive, right? Even the positive number remain positive, but a larger one. Okay, so simply, right, we'll perform that. Okay, fine. Now, is it sufficient? Is it good enough to represent our what do you call the error? Right? It's obvious. It's correct. Now you see, right? We are trying to on the along the x-axis, right? Along this x-axis, I'm trying to plot the d minus y value, right? So d minus y value is along x-axis. On the y-axis, I'm calculating the error according to the j equation given, right? So it's right. Take it as d minus y whole square. Okay, so when I say d minus y square, if the d minus y is larger, the d minus y square is going to be much larger. So more error, sorry, if the difference d minus y is more, error is more, cost is also more, right? It can be true for positive as well as negative. D minus y is negative. On the other side, you can see that it's going to attain a higher value, right? Very straightforward, very simple equation, right? Right. We can prefer using this, right? Unless and until we find another one which is used over there. Looks pretty complicated, maybe because of the log present over there and many terms over there. But anyway, we'll simplify that at a later stage. But anyway, we understand that this particular function, which is considered as a sum of the squared error technique or equation, is actually suitable, right? So d minus y is larger, I can find out more and more error being calculated. Cost is also more. So it means you have to use this error in some method so that more error corresponds to more weight update. I should somehow convert this error into that when I go for an update. Okay, depends on which algorithm we are using, but fine. Almost all algorithms are going to work in a very similar fashion. Get a bigger value of the cost, update more, right? It will try to update the weight, right? By a large number. So delta W, whatever we are supposed to calculate and put it in the weight updation equation is going to be large. Okay, so that's fine for us, right? So let's go to the next equation, right? So the second equation, you can see that I'll just show the equation once again. So there is a summation outside, but let's remove the summation. Anyway, I understand that I get some value. I keep on accumulating that for all the values of my training data. Fine. All right. So let's split. Now we bring a term that is called as a cross entropy. Why the word is used as a cross? Why it's a cross will come soon. All right, so let's try to denote that as whatever we have inside the braces, right? So minus d into natural log of y minus 1 minus d into natural log of 1 minus y. So notations we are pretty much comfortable now. I think d is right, the desired value, y is the current output. Now let's try to substitute values of d and values for various values of d like 1 and 0. So you just see here, if I put d equal to 1, this term vanishes, 1 minus d becomes 0. At the same time, if you put d as 0, this is not be present, only the second part will be. So you see that it's not actually pretty complicated when it comes to the simple binary classifier. I just have two values, either desired value becomes 1, desired value becomes equal to 0. Again, right, we can use it for other values as well. But as of now, in order to make the concept simpler, right, let's take that. It's a binary classifier. Almost all the problems we discussed so far, it's belonging to the binary classifier, right? So we were discussing outputs as 1, 0, etc. So under such case, right, now let's take this these two cases one by one and try to understand, right, why we prefer this, all right, rather than the other methods. Okay, now as we know that we are considering the binary classifier only. So under this binary classification, right, so output should be either 0 or 1, right? We have to use a proper activation function before getting the final y, so that, right, the partial outputs will be converted into ones or zeros. Okay, if it is not properly matching with the d, we are expecting some error. Okay, so this cross entropy function, right, normally it comes, right, with a sigmoid function or a softmax. As of now, we have never come across a softmax, right? In our discussion today, we are going to introduce that. What is the requirement? Unless and until I have some problem with the sigmoid or any other activation function, we don't need this. Okay, but anyway, so it's practically we will be using with the softmax as well. So I have used the term softmax here. Okay, so as of don't consider softmax there, right? So it's just a sigmoid as of now because we never discussed the softmax. But yes, right. Let's look at how this cross entropy works and what it's going to generate as an output whenever the desired value is equal to 1. All right, so you can see a graph here. So that is, it's the cross entropy function. E is equal to minus ln of y. So we expect d to be 1 because when d is equal to 1, then only I have, this function minus ln of y is what I can use. So I'm simply plotting the minus of ln y, natural log of y. I know that it is always between 0 and 1. So when you come closer to 0, right, you get a higher value here because d means desired value. Desired output is 1, target is 1, but my y is 0. Means what, I'm expecting higher error, right? You see, yes, error is going to be a larger value, right, as you can see here on the graph. All right, At the same time, let's say the y is equal to 1, right? So as you put that value over here, right? So the entropy comes closer to 0 as the y tends to, right? Now it should be very clear that, so though we are discussing only between 0 and 1, right? Between in the middle, because some of the activation functions may generate the values between 0 and 1, right? That's also going to work because in this, the curve is continuous. That's what we can see here. All right, so this is the case for uh, the target value being 1 and the output varies either 0 or 1. So when it is 0, it's error. I'm expecting a larger value as a cost value, so you can see that that's high over here. At the same time, since desired is 1, output is also 1, you see that the y-axis value is error. Error is minimum over this point. So that's what, there is no error. All right, so move ahead and let's consider the other part. So in our equation, we had a second part, that is when the d is equal to 0, I should be using minus ln of 1 minus y. So according to that, let's do the calculation and see what happens. So whenever the output is 1, right, I'm supposed to make that the d minus y is supposed to be 0 or 1. So you see here, when d is equal to 0 and output is also 0, I have lesser value. Error is pretty less. At the same time, right, if you, my required value is 0, but my output is equal to 1, I can see that error is pretty high, right? So we can actually write a code and implement that. But anyway, so I think we should be fine with this, right? So that's why I have not written a code for this. But anyway, so when you try to implement that, and if you want to use a cross entropy as your cost function, yes, this is what is going to happen, right? So right, instead of going for the squaring terms, we can even use this. All right, so what is the difference? The primary difference between the cross entropy and the other one is, right, you see the value increasing, right? As the d minus y increases, there is a quadratic increase in the value. So if it is like when the value difference is just 1 or 2, you have values like 1 4, but when difference is 10, you see the error or that cost function is too large, like 10. So if at all you have difference like 20, right, you can understand that that reaches 400, right? So like that. So whenever my input range, right, input data range, it's within some range, maybe 0 to maybe in an image intensity, if you consider as a range, it may vary from 0 to 255 possibly. So required value is something and you get some other value, so the difference is larger. If you use the first equation, you are going to get a larger value. So quadratic function generates a geometric increase in the value. All right. So the cross entropy function is right actually sensitive, more sensitive to the error. I just can understand that by just looking at it. Right? So other case simply keep on increasing the values, right? But the sensitivity is more over here. Okay, so let's have a quick look at the comparison, right? So this is the result we got when we try to run a particular code, right? With two cases. One implemented the cross entropy, second one implemented the sum of the squared error. So for a fixed number of epoch, if you fix a number of epochs to say maybe 50, fine, we can see that the cross entropy, right, is has reached the minimum, right, much before that. Whereas, right, around 50, we still have the sum of the squared error being presented, right? It's still existing over here, somewhere here, right? So, right, so fix a number, fix a, you can see that, right? The cross entropy, right? If you are using a cross entropy to give a generate a cost function, right? That is more effective, saying that that is more sensitive uh, to the error. Okay, all right. So that's about the various types of cost functions. Right? Do we have any doubts until what we have discussed today? Yes, sure, please. No. It's like, see, the equations are, we just have to understand the equation. That's why I brought the concept here. So in any method, whenever I try to use a library to solve some issue, classification issue or something, you are free to choose anything. There is no rule like that. Ultimately, you see, if normally the number of epochs are more than say 200, both are same, no issues, because we are not going to, normally we iterate 10,000 times or something. But these are the methods available. If you are going for very lesser number of epochs, then there may be a difference. Okay, only that's the case. But as the iterations go on, maybe after 400 or maybe something 450, 500, we don't see any difference at all. Both are same. Okay, so that's one thing. Again, there are various standard, what you call, networks design. Trained networks do exist. Okay, so they have been designed in such a way that each one of them uses their own method, right? So what are the options available? We want it. Like, right? So if you go for a Google's network, standard network, which can recognize 1,000+ objects, right? It's called as Google Net. Anyway, I'm going to come to that maybe in tomorrow's session, I guess. But you see, they have used a specific uh, what you call entropy function, cross entropy over there, like that. So any other maybe VGG net, they might have used this sum of square level, like that. Okay, so when we see that, in order to understand what they have done, we are discussing here. Otherwise, when we go for a huge number of data set for training, like a convolutional neural network based image recognition, classification, right? Ultimately, it does not matter. All right. So, in order to answer your question, no fixed guideline saying that okay, you have to use this, right? Because both of them will give you the similar result over a longer duration of iterations over training. Okay. I hope that answers the question. Yes. Sure. Any other question? No, entropy is basically it's the information. All right. So information is what basically how much information do you have? It's called as entropy, right? And the cross entropy is something like, if you go back and check, right? Uh, when d is equal to 0, the other one will give you the highest. Cross is the name given as a cross because desired is 0, in the sense if the output is 1, you are trying to generate a higher error. So that's the word cross here. Entropy is amount of information you get, right? So that's why we call this as highly sensitive to the data. So whenever data changes from just 0 to 1, right, we can see that, right, there is a steep change in the curve towards the end, right? So that's what is the meaning. So cross is just because we are understanding that okay, 0 is the required one, I'm getting 1 as output, so I have a higher error. So that's the cross. Entropy is that you are getting a lot of information related to okay, there is an error. Okay. All right. Any other doubt? Okay, so far we were discussing about the binary classification, simple classifications. In order to say again, in that we might have discussed about linearly separable, non-linearly separable classes. So now we want to think, right? What if we want to go for multiple classes, right? What should be the architecture of the network that we are supposed to design over here? So what should be the requirement? So let's consider a simple case, what we see here, right? So we have three different data sets which can be plotted on, let's say, on a graph, right? X and Y coordinates, but they belong to depending upon the location where you are able to plot, we get different we'll be able to visualize different clusters over there. Let's say, okay. So one such example of the data, such a data may not be a multi-class, but where we can plot and visualize practically is the formant frequency, right? Under the speech recognition. So when uh, any person speaks, there will be at least two fundamental frequencies with which the person is going to speak, right? So we can plot f1, f2, two values you get, right? F1, f2, you can keep marking over there. One of the fundamental application, which was it's a very pretty older application, just to identify male or female, right? So it's one of the applications. So we have higher frequencies f1, f2 for female, and male voice will have lower frequencies. Okay, so like that. So if you have say three people talking, right? A, B, C. I can try to see there are three classes now. Whether person A is talking, B is talking, or C is talking, I can try to identify, right? By using the formant analysis. So just calculate the formant frequencies and plot. Design maybe any neural network if we want to go for neural network based, or if we want to go for any other machine learning algorithms, also fine. Like doesn't matter. Like you see, this example is actually something related to that example. You want to identify this. It's a simplest case of a speaker recognition. All right, so we have three different data set present over here. You can see something marked with a circle, some points are marked with rectangles, some other points are marked with the triangles. So now uh, my question is that what changes do you want to make in the networks we have studied, we have been discussing so far, right? Maybe take that there are each point has two coordinates only. It's not a multi-dimensional data. So number of input layer, number of neurons in the input layers you can decide. Okay, just to say that I'm saying, so each point has two coordinates, x and y. All right, so you need to decide how many number of input layers, how many number of neurons in the input layer, how many hidden layers you may expect, or how many number of neurons in one layer if you are going for that also you can decide, and how many output neurons you require, right? I want you to think about that, and if you have an answer, please put the answer in the chat. Okay, so input, right, this number, output this number, hidden anyway we can vary, right? I don't want hidden part. Okay, input how many neurons, output how many neurons, you try to decide, try to think about that, and please put your answer in the chat. We have say 1 minute time to think about that. From whatever basics we know so far, I think we should be able to answer that. Just make a guess. Okay, so we have one answer saying that 5 into 3, 5 into 3 in the sense 5 inputs, 3 outputs. Is that so? And Jyoti says 3 inputs, 4 in hidden, and output 3. Okay, output will be 3. Says Sneh. Yes. Okay. So you see, input, it's pretty straightforward to decide. Say that each point, each data point has how many values to be represented. In the sense, one point can be represented using, as I just mentioned, two values, x and y. So to take x, one neuron, to takes y, one more neuron. All right. So input two. Fine, right? Let's proceed further. And again, don't consider this diagram where I removed the hidden layer, right? I didn't want to discuss a hidden layer as of now. So anyway, don't worry. So hidden layers, yes, since it is two, you can go for more than two. So anybody answered three or more than three, like three, four in the hidden layers, absolutely fine. That's fine. Okay, you can keep the number of neurons like that. Okay, So coming to the output, now you see, previously we either used just one neuron because output was expected one or zero. All right. Now we slightly move ahead, right? And we, since the number of classes are three, right? We will be using three different neurons. Okay, on the output layer you can see. So you can consider this part, right? So whatever you see here, which provides the direct outputs over here, right? So this part is the output, right? And we are considering three outputs. So here we actually are supposed to use a hidden layer. Assume that we eliminated one. We are not using, not considering that as of now, just for simplicity. Okay, all right. So yes, right. So number of outputs are three, right? Most of you have guessed that. Okay, and that's the right answer. Now, so how do you generate the data set, right? So because this is going to be a supervised learning, and in the supervised learning, I need a specific way in which I'm supposed to represent my data set. Yes, do you have any question, Nitin?
Yeah. So actually, just I was just thinking like, okay, for output,
Hmm.
uh, can't we use like okay two neurons itself, because it's like okay 0 1, because it can have like okay four different values and then you can interpret also.
Correct, correct. That's right. That's right. Uh, but this, what direction we are moving here, right? This implementation is much easier than that. Okay, so only that's the
Okay.
reason, right? So yes, what you told is right. If you practically try to implement such a neural network with two outputs, because yes, as per the basics, we know that if you have two, say binary values that you can represent, you can generate 2 to the power 2. So four classes are possible: 0, 0, 0, 1, 1, 0, 1, right? Yes, perfect, right? Valid question. But the answer to that question is that what method we are using now and what is the output expected. Now you see, immediately, maybe the next slide, I will show you the expected output, right? So
Okay.
that expected output is pretty simpler compared to the one which we generate if we use only two neurons. Okay, only that's the reason. This is much simpler and easier to implement. Number of calculations are also less only, not a huge number of difference in that. So implementation wise, it is easier. Understanding is also easier. Equation is also going to be pretty much simpler in this case. Only for that reason, we are trying to generate like this. And this same concept we are going to extend even if you have 10 classes. Say digit recognition like 0 to 9. We are going to use 10 neurons in the output layer. Okay, we are not going to reduce that number to a smaller number. Okay, right. I hope that that's clear. Yes.
Yes.
Sure. All right. So let's come to the requirement. How am I supposed to write my data set? Because data set should be proper. Only then the training happens properly. Right. So as of now, let's consider the various XY coordinates, and what I try to write, maybe 5 comma 7 belongs to class 1, right? So another number 2 comma 4 belongs to class 2, etc. This is the general way of writing that, right? Because class 1, class 2, class 3 is fine for us, right? Human understanding, it's fine, it's fantastic. Even if you write ABC over there, right, those letters are supposed to be converted into something so that machines can understand. All right. So anyway, so in other programming languages, we have to explicitly convert them into, right. So if you use, maybe you convert into use ASCII letters, etc. Okay, that will be done by the compiler if it exists. But here we try to, in this case, we are not going to that level. We try to keep this concept as simpler as possible. All right. So what we try to do, since class 1, class 2, class 3, because of the three classes we have, our intention is that the three neurons which you are using at the output layer, right, it should be able to understand, right, which neuron should be firing or should be activated whenever the data belongs to class 1. So since we use the three neurons at the output, it should be very clear by this time that, okay, one neuron per class, obviously, correct. So what is expected? The expected output is now, like, only one of the neuron will become one, others should remain low, 0 or minus 1. So whichever class this data belongs to, only that neuron will fire. that neuron will activate with the output value equal to 1. Now we need to make sure that, okay, this is going to happen at the end, right? So before that, let's see. So as per our requirement, my data will come followed by which class it is. It should come whenever I try to represent that data in a particular date in the format of a data point. So this is how the rough uh, data representation looks like. But anyway, we understand that this is not going to work. Machine will not understand this, right? So what we do, we'll apply this logic. Like since there are three neurons, class 1 has 1 0 0 because 1 is that particular first neuron being activated. Other two neurons are 0 0, saying that they stay low. Similarly, class 2, we can see that it is 0 1 0, class 3 is 0 0 1. Okay, pretty simple, pretty straightforward. This only thing is that I should check that whether my activation function is capable of doing this or not. All right, only that's the problem here. I hope you understand, because if you use sigmoid, right, and the output value, right, is there. Okay, I'll ask you a question on that itself. So my question, can you use sigmoid? Okay, so just think, this is what we are talking about, right? So the representation we can see below here. Okay, so three neurons are there, right? So the three neurons, if it is the data set is class 1, this is the expected output, right? If the next value, this is the output, right? If it belongs to class 2, class 3 is like this. So we can see that one of the neuron will fire. Now my question is that, right, will you be able to generate such values for sigmoid? Because so far, right, everything was sigmoid everywhere. So can we retain that, or what's your suggestion? If possible, you take one or two values, like let's say that first neuron gives a 0.5, second neuron gives you, because right before that it's a simple summation of w into x, right? Any value might come. So positive, negative, you can say, right? You can assume some values. One of them gives you a high value 0.9, second one gives you a mid value 0.6, last one gives you a smaller value 0.1 or something, and you can think of that, right? What's going to happen? All right, so keeping that in mind, right, just think about that. Let's bring a specific terminology which we are going to use widely in the throughout the course of machine learning and deep learning, is called as one hot encoding, right? So whatever we did now, right, this whole concept, we had class 1, class 2, class 3, we try to generate a either a binary sequence or something in terms of binary, right, representation. Now we are, let's say, computer is going to look at this particular class 1 data as a sequence of binary numbers 1 0 0, right? Class 2 has 0 1 0, class 3 has 0 0 1. So this kind of uh, encoding for our classes, it's called as one hot encoding. That's one hot encoding is widely used rather than the one of n encoding, right? There is another term. Maybe if you refer various reference books, you might find the 1 to n also, 1 of n also. But widely used in the programming, the built-in functions in Keras, TensorFlow, etc. They use this word, one hot encoding. Okay, there's a function. Just you have a data set, you can simply call this function, it will automatically get converted into the binary sequences. We don't have to write a code for this. All right, class 1 do this, class 2 do this, don't do it. We don't have to do it. Machine, I just have to specify how many classes I have. Okay, let's say I want to do an analysis of the human emotion, right? You have a data set, text data you have, or I'll keep it more simple. Let's say I want to classify the Amazon reviews, right? Based on the reviews that we read. It's a NLP case. We are going to discuss on NLP as well as we will be doing some projects in the upcoming NLP session. All right, but just to give a hint, right? If you have so many classes present in your data set, simply just mention that perform one hot encoding of this data set, and right, generate 4 classes, right? So right, we'll be writing like, okay, positive review, negative review, right, neutral review, something like that. We may have a column, but it's in the text format. Machine will not understand. You have to generate a binary sequence, right? So that will be done using this particular function. So just remember this word, Okay, so we will be using that when we call such functions. All right. So once you perform this one hot encoding, right? Once we implement that into our data, right? What we get, that the data will be converted into this particular format. Now you see that according to the classes, you may have various values present over here, like 100 particular class, 001 class number 3, 010 class 2, and so on, right? According to the class, we have a particular case. Okay, so that's what is the case. So I come back to my question. So can you use the sigmoid function for generating this kind of data? Right? So previous cases, you remember, if you remember, we had only one neuron. Softmax, depending upon the value of your input to the activation function, it will either, if it is present on the right side, generates a positive value, left side, it generates another value. That's all. Pretty straightforward. But now you see, we may have, right, different values coming from each of the neuron. Right. So when I use, say, both neurons are giving you a positive values before the activation function, 0.6, 0.9. What happens? If you use softmax, both will generate 1. So output will be 110. Let's assuming that the lower value, the third neuron is generating a negative value. Okay. If all the three are positive, I have a problem. All the three neurons will fire 111. That is not at all expected. Right. So I'll show you the issue with that now, right? So this is the problem, right? As you can see here, right below, right? That's a problem. I'm coming. So let's discuss the basics. Why do you need to change now? So we bring in a new activation function, right? That's what came today in a earlier topic, which is a softmax, right? So, right, we understand that if you have an output value, partial output, that will be converted into a range, right? So we know that it may be -1 to +1 by the sigmoid function. So far, we have used this successfully for a simple binary classification, 1 or 0 case, right? Just now I told why it worked very fine, because there is only one neuron, only one input will come. You just have to tell that whether this input belongs to this side or this side. So it worked very fine, right? But right, in a multi-class scenario, right, since we are using n number of, if my data set has n classes, I'm going to use n number of output neurons. For this case, 3 classes, 3 neurons. So that means, right, if I use a softmax, I may get multiple ones in the output, which is not at all the desired case, right? So though there is output available in my function, right, I may not be able to generate that. So softmax is something like it's going to consider the maximum value of the output, but it's not just finding the maximum. That is again may not be sufficient. Okay, so what it performs, it actually so let me go back to the drawback of the sigmoid once again, so that I'll update at that and I'll come to the software. So if you are using, say, 3 neurons in the output layer, and all the 3, if we use the sigmoid function, what happens? There is a equation, 1 divided by 1 plus e to the power minus x. X is my input. This function will be the output. Okay. So are you considering what is the value of the other neurons present in the same layer? It's not. It's not. You simply, I have a x1, x2, x3. So it is applied. Phi of x1, you get output. Phi of x2, get another output. Phi of x3, you get a third output. But those 5 values, 5 functions are never considering what are the values that are coming right on the other in the other neurons. This is actually major drawback, because only one of them should be activated, right? Because my, depending on the data set, my expectations are. So in such case, right, that becomes a drawback of the softmax. So sorry, not softmax, in sigmoid, my mistake, I correct. It should be the sigmoid which has a drawback, which does not consider the outputs of the other neurons. All right. Now, when we want to incorporate the one particular activation function which is intended to calculate the maximum value, we also should bring in the concept that while calculating the specific value that is going to be generated as output, you should be able to consider what are the values of other neurons generating that also on the same layer. So like if I want 100, only that neuron should generate highest value so that you can take a softmax, right? So other neurons will generate a value for sure, but they are lesser than that so that you can apply the maximum function to that. Okay, so how it is going to be done? Let's consider that there is a value. All right, so the value of that actually three neurons are actually generating partial outputs are 2, 1, and 0.1. Right. What we do if at all you are using the sigmoid function, 1 divided by 1 plus e to the minus 2. 1 divided by 1 plus e to the minus 1. Next, 1 divided by 1 plus e to the power minus 0.1. That's all, right? You are not considering other, but here you see the equation, right? For the first neuron's output, it is e to the power that value. Divide, you look at the denominator. All the three are using the same denominator. In the sense, the values of other neurons are also being considered. See, e to the 1 and e to the 0.1, they are the other neurons' responses, right? So e to the 2 is this, the current one. Now you see, right, what the output we get. We get for the first one 0.6590, right? So at the same time, right, for the second one where the value was 1 corresponding to the second neuron, you get a value 0.242, and for 0.1 you get 0.0986. Now you apply max to this, which is a maximum. Only that will be 1, others will be 0, 0. Now I am getting 100 here. This is because my first neuron generates 2, which is the highest one, then 1, then 0.1. So this is happening when we, sorry, this is going to happen whenever we are using the softmax function, because softmax considers the outputs of other nodes or the other neurons as well, so that we can consider this to be a weighted, right, calculation, right? So it follows the weighted calculation of the output values based on the inputs, not only considering the current input but also current node, but also the other nodes or other neurons in the same layer, because of which we are able to generate the required outputs in the format like only one of them should be 1, all others should be zeros, right? Irrespective of the number of classes you have. If you have 10 classes, only one of them is allowed to become high. All the other neurons output should stay low. All right, so this was a requirement because of the multi classes we have, right? So since we try to write the output in a specific way where only one of them is 1, others are zeros, we don't have any other method, right? We have to go with this. Okay, so that's why. So remember, when we have multi classes, right, multiple classes in our data set, what is the output activation function? Always it is softmax. Go to any complicated neural network or any complicated deep neural network, right, or deep learning algorithm which incorporates the any of the neural network methodologies, right? You will see that the final layer is always softmax, right? Now itself you can go and check anyway you want, right? But anyway, right? So that's the concept, right? So why do you need a softmax? Answer is this. Okay, do you have any question with whatever we have discussed so far?
Just one small, yeah.
Yeah, yes, sure.
Whether
Yes.
small, yeah. So basically, see, if it's a multi-class, then we are saying like, okay, softmax. What about like, can I even like instead of a sigmoid, can I use a softmax for even binary?
Softmax
Will that
for
have an impact?
yeah, yeah. So softmax on the binary, yes, possible. Yes, you can. No issues, right? But preferred one for a binary cases, we prefer using the same method. That's all. Okay, that's a convention to use the same. But definitely, right?
Yeah.
So if you will always have a something like right out of. So I have only one output, so you don't have to use the softmax there because only one value will come, right? Binary class
Yeah.
means only one neuron at the output. So it generates only one. I don't have any other neuron to compare with, right? To make it,
Yeah.
to find the max of something, I don't have any other value. Only one value will come. So we don't prefer right? We still prefer the sigmoid only over there, because sigmoid will tell that, okay, this value is bigger than 1, so your output is 1. The input to my activation function is lesser than 1, so output is -1. It will tell there itself. Okay, so that's
Yeah.
what is the preferred way. All right.
Yeah. Thank you.
Okay, sure. Any
Sir, a
any other
question.
doubt? Yes, sure, please.
Yeah, sir, why for a given time only one neuron will be high, other should be zero?
Okay.
What?
Yes, sure, sure. I'll answer that question. So you see here, now I have three output neurons, right? So we have chosen three neurons in the output, right? If the idea is that if my data set belongs to class 1, only one neuron is supposed to be high, because 1 means, okay, this belongs to that class. That's what is our expectation. Desired value, the target value will be 100. For example, consider this data. So you see 5, 7. This belongs to 100, saying that, okay, this 5, 7 belongs to class number 1. Okay, I cannot write class 1 or class A, etc., because machine has problems in understanding. So I have to go for a binary. So how do you represent that in the binary case? You see, this is the easiest way. Anyway, you can go for 2 neurons only, which will generate 0, 0, 0, 1, 1, 0. But that is more complex, right? That becomes more complex. Now, since our assumption is that for class 1, this is the case, we expect only one neuron to generate that one, other two remain low, saying that, okay, this data does not belong to our class. Second neuron is expected to fire only when it is class 2. You see, this comes 1 only when the data belongs to class 2. Similarly, third neuron fires only when the output comes from that neuron, which says that it is coming from the class 3 data. So irrespective of which class it is, you see, only one of them will be high. Okay, other two will be low. So you have to read column wise now, not row wise. Okay, so corresponding to three of them, right? One of them will fire for a given data set when you do the testing. Okay, is that clear?
Okay.
Or do you have any other doubt?
So here the all the outputs are into binary. So how should we classify that this for neuron 1 this is class 1 or class 2?
Sure.
Maybe can we have a real example so that it will be easy to understand?
Yeah, I'll come to the real one will be coming, because data set will be not very simple fashion. We may have to use, right, a few more columns in the data. That's why, just for explanation purpose, I'm keeping it simple, because if we go to a practical example, this will be more complicated to understand. That's why directly I'm not jumping into that. But yes, I'm coming to the practical example. All right.
Okay.
So I'll answer your question. Just to,
Yeah.
you asked that, how do we classify? Right. Let's go to this example. So the final output, what you get before the activation function, is this V. First neuron generated 2, second neuron generated 1, third neuron generated 0.1. Okay. Now I pass these values into the activation function. See, the activation function is changed now. It's not the previous sigmoid, it is the softmax function. Softmax function calculates something like this. Okay. When I have 2, it is e to the 2 divided by e to the power 2 plus e to the power 1 plus e to the power 0.1, because we want to consider other neurons outputs as well. It's a weighted value. Whichever gets the highest one, only that should generate a highest value. Others should stay low. So you see here, the 1 and 0.1, other two neurons, which are the neuron number 2 and neuron number 3, in the output layer, they generate 0.24 and 0.09. And the one neuron which actually generated the highest value, that generates 0.65. Now what you do from this, take the maximum. Apply a max function to this. What happens? Max of this means it says, yes, this is 1, this is not max, this is not max. So you got 100 at the output. Okay, so I just wanted to show the calculation here. That's why I have it in here. But the name is softmax. Softmax will actually takes a max after this step. In the sense, whichever is maximum, only that is 1. Others are 0, 0, saying that yes, they are not maximum. Now you see, whatever the partial outputs you had, they got converted into 1, 0, 0 according to this case. This particular example is for class 1 only. If at all an output that might come from the class 2, maybe the 2 will be shifted to this, 1 will go to the other location, can be something like that. Only that neuron will generate a highest value. Okay, I hope that is
Yeah,
clear.
yeah.
Yes,
Clear,
yes,
sir. Clear.
yes, yes. Is there any
And
other doubt?
just a small
Sure.
doubt.
Yes,
In the previous diagram,
Huh.
where the three neurons are indicated,
Yes, yes.
so the inputs of this, all the three neurons will be independent. It's not from the two inputs. It's independent three
Actually,
inputs.
yes. There is a hidden layer present over
Okay.
here. Okay, so there will be a hidden layer, but as I mentioned earlier, just to
Correct.
make things simpler here, because our discussion is not towards the how the hidden layer works or how
Correct.
the weights update. So I neglected that part. Okay, so I
Agree.
have
Agree.
written that in the sentence also. Even when you read this notes, you will understand. Okay, I mentioned that. Okay, I have neglected the hidden layer for simplicity purpose. Right. So as you told, yes. So they will come from the hidden layers. The input to all these three neurons, right? They will be coming from the hidden layers. Right. You may use 1, 2 hidden layer or single hidden layer with more number of neurons, etc. Right. That is left to us.
Okay, sir. Thank
All
you,
right.
sir. Yeah.
Yes. Sure. Okay. So let's move ahead. Now, after the softmax function, all right. So right, this is again it's something like an assignment for you. You don't have to submit nothing, right? Just try to implement this from our previous knowledge, right? What is the change that is supposed to be done is only the output number of neurons in the output will change. I tried to give a graphical representation of what you are supposed to do, right? Please try to do that. Anyway, if you have doubt, anyway, I'm there to answer your queries. Okay, so this is the target, right? So just try to understand what is the question here, right? So you're supposed to implement a multi-class classifier. So how many, what's the question? Let's see. We want to recognize the digits from the input binary images. So now the question will come, I don't have a image, I don't have a data set, no issues. We'll come to that. So let's try to keep it very simple, only 5 classes I need. So the digits that I'm going to give as input is 1, 2, 3, 4, or 5. One of them will be given as input for training as well as testing. So, right, 5 classes, which makes things very clear how many number of neurons in the output layer. Fine. So that's very clear. I have 5 neurons in the output layer. Right? The rest of the things are yet to be decided. Right. Now, so I'll come to the specification of the input. Though the question says that input binary image, right? So input binary image means it will have 1 or 0, which means I don't have to have an image. I can create a matrix, right? So it's that simple. So input will be a simple matrix, right? So you see here, consider the data set now, right? So you can see a 1, 2, 3, 4, 5, right? Those are written here. So slightly trying to make it slightly moderately complex, not very complex. This data set is again not very complex. You will understand why. So what is the size of this data set or size of image? If I ask, right? If I ask what is the size of image, can anybody answer? All the 5 are of the same size. So what is the size? How many pixels are there? You can answer number of pixels of this image, or even you can answer what is the size of the matrix that I'm going to write. Anything is fine. Just see this, see the 5 different samples I have shown here and try to answer me that question. All right. So what is the size of the data set? Okay. Size of each image to be specific. It's a 5 to 5, right? So I can see that every image has 5 rows. Each row has 5 columns, right? Now, if you are trying to write 1, right? For example, I want to pass 1 over there. Wherever you see dark pixels, right? It's left to you, right? You can say that, okay, only those values are zeros, all other values are ones. If you are looking at the brightness value, okay? But for human understanding, we prefer the other way. Wherever you see the letter, the number present, you can make it 1, 1, 1, 1. Other values are zeros, right? Left to you, both will work. Machine will be able to understand both of them, right? So you see, for example, if the machine, if you want to make it human readable, then the first row of my matrix corresponding to 1 will be 0. That is corresponding to the bright spot you have 0, 1, 1, 0, 0. Because wherever you have 1, 1, there is, you have written something. Then the second row will be 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0. Just to give a matrix, that is your data. Just it's actually, it's not a complicated problem at all, basically, right? Maybe you have to do a little bit of thinking about the representation in terms of numpy, etc. Right? So maybe that may take some time to get adjusted, because a little bit of numpy experience is required. How do you write, represent, etc. Because the program, the previous class, I think we faced some problem. I had to convert something into an array, and then only it worked, right? Whenever you multiply, etc. So such issues will come. Only those issues will come. They are going to be present in each and every program that we write. Okay. Other than that, data set is very simple. Just recall, previously the data set was just one row. Like if 0, 0 is there, class 0, 1, class 1. Like that we use. Now it's not that. If this is the matrix, it is class 1. If the second, so you can see that for the input image 2 of class 2, this will be the data set. You can write the similar numbering over there, right? Like ones and zeros you can use. So it should be very clear now. So what is the input, right? So there are 25 points, right? I'm going to give all the 25 points at once to the machine. So think about the programming perspective. The whole matrix will go into the machine at once. So you have to use 25 nodes. Each node will, each neuron will be in the input layer, right? 25. The first one will take the first this point, right? Second neuron will take the next one, third neuron, fourth neuron, fifth neuron, and the last one, 25th neuron. That's all, right? So depending upon your programming way, right, you may have to convert this, you may have to reshape, that's all. If required, you do that. Otherwise, there are methods which can work even without doing the whatever reshape. Okay, so left to you. You are free to choose what approach you are going to use. All right, that's fine. Now, right, yeah, already I mentioned that 5, right, because 5 classes you have, right? So requirement is that you are supposed to use a softmax at the output. So in the layer which is maybe it's a hidden layer or something, you don't have any issue, right? You are supposed to use the sigmoid function. All right. So these are the requirements. So the roughly the network looks something like this, right? So this size is 25. Okay, you are supposed to use, I know that if I'm going to use 1, right, so go with 1, don't go for more number, because I know that it's going to work for one neuron, one hidden layer itself, but definitely number of neurons should be more than 25. Okay, so maybe start with 50, let's see what happens. All right, so keep more neurons here. 30 should work, okay, but as a whole number, simple number, I went for 50, that's all. No specific reason for 50. You can go beyond that, you can go 100, right? So etc, right? So decide and implement. Already you have a code, right? So how to decide what should be the size, how to give input. Only input size is different, that's all. That's the one thing to remember. Other than that, here you see you have 5 neurons. So corresponding to each of the class, you can see here what is the output that is expected. You can see, right? It's pretty simple. What just now we have discussed, same thing has been shown here. I have 5 classes, and corresponding to the input that you are providing, right, each of the in each of the case, only one of the neurons should fire. If I give 1 as the input, you see only this neuron fires. All the other 4 neurons are zero. This was the expectation, right? Same thing happens. So for it, if you give input as data 2, right, it should only that second neuron should be high, other neuron should be low. Same 3 for this case, 4 for this case, and okay. So do you have any question on this? Anyway, you will get the the material, right? Over there also it will be there. And if you want to start working today itself, please take a snapshot of this, whatever I'm showing, right? I'll go to the question part. Yeah. So.
Oh, sir, I have one question.
Yes, sure,
Actually,
please.
yeah. Actually, I'm getting confused. Like softmax function, as you told, it will consider the weighted sum of the input from all nodes, right?
Correct.
So, but uh, like in the case of multi-class, we are not like at the output node, we are not considering the input from other node. I think.
No. I'll answer that question. Okay.
Okay.
So you see here. See, in the previous example, this example, we have 3 nodes, correct?
Okay.
3 nodes. Let's consider these nodes are generating an output that is equal to this V value. Yeah, it's here. So you see, first neuron 2, second neuron 1, third neuron 0.1. Is it okay? Right?
Okay.
3 neurons you saw in the just now I showed a network, right? So those 3 are generating 2, 1, 0.1. So
Right.
according to this activation function, that is a softmax, right? You are going to do this particular calculation. Right. In this calculation, e to the 2, that is corresponding to this output. Okay. But you look at the denominator. I have e to the 2, e to the 1, e to the 0.1. From where it came? It came from 2 came from this, 1 came from this, and the 0.1 came from this, right? So you see, this output actually takes care of other 2 also. Is that clear, or do you want?
But if the other two output are of different class, then why we are considering it?
I want only one output should be high. Correct? If you apply this to the sigmoid function, both of them will generate high. It's like 110 possibly, right? Which is a wrong classification, right? I am expecting 100 or 010 or 001. Are you understanding the problem definition? You see, I am expecting only this. I should not generate 110. That's a wrong class. I don't have any of the class with 110.
But as you told, only one neuron will be active, right?
Yes.
At the time.
Now you see at this time, you consider this column, right? First column.
Right.
Only one neuron is 1. Other 2 are 0, right?
So if one neuron is active, then other two will not produce any output.
If other 2 are not, whatever value other 2 generated, what we did here, just please try to understand here, right? So you see, first neuron generated this, second neuron generated this, third neuron generated this according to the software. Okay, but I am considering only max of them. Only max will be given as 1. Others, or any number of neurons may be there. All the others will be given 0. So this is 1, this is 0, this is 0. That's what I want, right?
Okay, I got it.
All right.
Right.
I hope that is clear.
Right.
Yes.
Right.
So that's what is going to happen. Now, when you write your own code, there will be 5 neurons. Okay. E to the power something divided by e to the power 5 terms in the denominator, because you are considering all the other 4 neurons as well. Okay. Only that is the part which is expected. Okay. I hope that is clear.
Yes.
Sure. All right. So with this, we'll take a break now, and we will come back at 1:45 and we'll resume. All right. Okay.
Oh,
Let's
okay.
take a break. We'll join back at 1:40. Right. Do we have any doubt with the whatever we had in discussing?
Sir, yeah, I have some queries.
Yes, please.
Just understanding the basics, like how we are getting this data input. Suppose these digits are indicated visually. Now, how the computer is getting that data, whether we are feeding with a camera or manually, or how? And if so,
Okay.
then this identification, I don't think this neural network kind of a technique is required to identify this. There are many easy techniques also, but maybe just I am more interested to how we are getting this data input to the computer.
Okay. So again, just remember in this particular case, the input is not an image. Though the question says input images, input binary images, it's mentioned specifically that input binary image, just to give a hint that you can generate this 5 into 5 as a matrix, right? Simply create a matrix A equal to, right? Just give these values. What are the values? Like this is the first value, if you see, that's actually bright color. So there is no one, has no, it's present, is it's not present in that location. So over here that will be 0. So 0, wherever you see a black color, that could be 1. So 0 1 1 0 0. You see, you are writing a matrix actually. So the input is a matrix, okay, corresponding to all, each and every 5 digits you have, you create 1 1 matrix, right? This is actually, right, only difference between the previous code we wrote and this code is that the input is a matrix now. Previously it was just one row. Every time you give a training data, that was a row once. Only one row used to go inside the machine for a learning purpose. But now it's different. Right, what we are passing is a complete matrix. 25 points will go as input. So anyway, when we have an option to, it's left to the programmers. Here, what we can do is you first generate a matrix 25, 5 into 5, 5 rows, 5 columns for 1, another for 2, another one for 3, 4, and 5. So you have 5 different matrices to be created, right? Since it is a binary, right, you can consider that as image, black and white image. That's why the name says input binary image. No need to take a photograph, no need to do this thing. It's pretty straightforward. Okay, so in this case, it's just that. That's your input. But giving an input, you ask another part of the question, how do you feed it to the machine, right? So to answer that part, we have basically two options, right? You can make sure that the samples what you have, right? Each point is a pixel. So there are 25 pixels arranged in the 5x5 format. You can feed it as it is to the machine. All right, 5 into 5, you can feed it as it is. First option. Second option is that you convert this into a row matrix or the column matrix, in which case the problem becomes pretty much similar to the previous problem. Previous problem had only 2 points. Okay, it was a one row, 2 column problem. We solved a classifier, right? We also had written a code for that. Was only 2 elements were passed to the machine. Now, if you convert this all the 5 classes into a row matrix, it will be 1 row 25 column matrix. Only size increases, that's all. Other than that, nothing will change in your code. Right? Maybe slight variations, right? That you need to take care. But other than that, only change in this whole problem is that one is the input, which has more number of points, and one more is the output, which has there is no single neuron in the output, 5 neurons in the output. Okay, I try to answer your question. Is that clear? Do you have any other doubt?
Yes, sir. Clear.
It's clear, right? Okay, so no need to take a photograph, no picture, nothing. Okay, simply write a matrix. Right? Ones and zeros should be present.
Correct. Yeah.
Okay. Yeah. Do we have any other doubts with respect to whatever we discussed so far? Okay. So, so initially, I think we had a question when we started the whole discussion of the neural network, right? I think we somebody raised this point there related to what's the use of adding more and more hidden layers, right? What happens if I increase the number of layers? Okay, so I think I was able to answer only 50% of the actual answer because we never discussed about the in-depth of the concepts. Now, but now I can answer that because most of the topics we have to cover. Right. So this topic is what are the improvements in CNN compared to a simple neural network or compared to a simple neural network or the neural network with more layers. Okay, more hidden layers. You can call it as a deep neural network as well, because number of neurons are more over there. So that's the point. I have more neurons present, right? Ideally speaking, so we think that, okay, if I improve the number of hidden layers, right, machine should be capable of learning more, and result is expected to improve, right? And maybe if the metric used for the performance analysis is accuracy, maybe we think that, right, accuracy should increase, right? So, but actually what happens if you simply keep on increasing the number of hidden layers, right, we actually face problems instead of, right, getting a better results. This is obviously because now we have enough background just to give a comment that why it is not, why we are getting more and more problems, because machine is not getting trained properly. So that's what is the first point mentioned over here. If you have a neural network and you increase the number of layers, deeper layers, right, they yield poor result, right, because the network is not getting trained, right, properly. Initially, you had lesser weights to update, maybe that got updated, right, efficiently, right, but as and when we increase the number of neurons in a layer more than required, right, too much more than required, not like I was expecting 50 neurons, I gave it as 100, doesn't matter, that's okay. Only 10 neurons are enough, 10 layers are enough, I went for 500 layers, then you feel this problem. Okay, then we are going to face this, right? So what are the, how CNN or the deep learning concepts where we use the neural network, right, where we use the deep neural networks, right, they have overcome all such issues, right? So basic problems you face when you simply keep on increasing the hidden layers, right, when that concept is compared with the deep neural network under the deep learning, which uses lot more than a lot more neurons compared to the first case, right, they still perform better, right, they still give you a good accuracy compared to that case. Why? We are going to see that. So what are the various improvements that have happened under the category of deep learning, where we use, right, the starting from convolutional neural network, we have many other networks to study. So how they are performing better, right? So the first problem, when I'm simply increasing the number of layers, and right, I have 10 layers, I increase to say 50. What exactly is going to happen? The first problem that we see, right, that we face is called as a vanishing gradient problem. All right. So initially people had no idea about this. So they thought that, okay, I have so many layers and I increase the layer, I'm expecting a better performance. Pretty straightforward, right? But that's not happening. So people could not understand why so. So the problem is that the answer to that question, why, it's because of what is called as a vanishing gradient, right? So let us consider the back propagation we considered in the previous class. So in case of a back propagation, we understood that final layer, output layer, we calculate the delta value directly. Calculate an error, and from the error, calculate the delta. So propagate that delta backwards by multiplying by the transpose of the weight connected to that layer. Transpose into that, you get the error of your previous layer. It can be a hidden layer or any other layer, doesn't matter. So if you have, say, 3 or 4 hidden layers, pass it backwards in the same fashion. So output to the last hidden layer. From that hidden layer, calculate the error of the previous layer, convert that into delta, again pass it to the previous, and so on. You see the error is propagating backwards. Every time I see, I'm calculating the delta value. Right. So this delta calculation is important, right, because my each and every equation of weight update uses this delta. Using the delta itself, we are calculating what is called as the delta W, change in the weight. Right. So though the change in weight part requires a specific algorithm, right? You may use any algorithm that is present, but doesn't matter. So as far as our discussion is concerned, we'll stick to the delta learning tool. Because we have used it, we have programmed that as well. So let's stick to that. We have that particular equation wherein I use the delta values calculated to calculate the change in the weight of that particular layer. Okay, now when you have more and more number of hidden layers, what happens? I calculate the delta for an output layer, right? From there, I'm supposed to calculate the delta of the previous layer. From there, calculate the previous, and so on. Right. Now, when you have a huge number of hidden layers, this delta is actually the final delta is a bigger one. All right. So the value before that will be the delta value, because that is the error. That's a portion of error, or you can calculate something like a proportionality here. What proportion of your final output, which is an error right now, right? I didn't get a d and y same. I get a different y, which is not equal to d. So there is an error. What portion of that error came from this particular neuron is what I'm trying to calculate. Right. So, right, we are calculating that by using the differentiated or the derivative of the activation function. So we know that what is the activation function used in the hidden layers. Output we are fine. Now we know that if it is a binary, I'm going for sigmoid. If it is multi-class, we'll go for the softmax. All right. Yes. Fine. What about hidden layer? We are still with the sigmoid, correct? So if you recall the sigmoid, right, and you try to calculate the delta value of the other than the first layer, from that I calculate a second layer, from that I calculate a third layer. What do you expect? That delta value which comes to the previous to that, much before that, etc. What do you expect? What happens to this delta value? Is it going to increase? Is it going to remain same? Is going to it will vary, but do you expect it will keep on reducing, or it will be simply fluctuating? Like maybe I get a bigger value now. Next value will be slightly lesser than, maybe depends on equation. Next once again increases, then decreases, etc. So, right? So just apply the equation. If you are able to recall the equation we used earlier, maybe you can think about that. I'll give you another approach to come to this answer slightly later, maybe in the next slide also. Okay. So yes, Jyoti. So she's saying that it's going to reduce. Yes, Sneh. So because I'm trying to calculate what portion of output came from this. Okay, this particular layer has, let's say, 2 neurons. What portion of these two error, right, error of these 2 neurons came from the previous layer? That's what it will be less, because there will be, maybe you have more neurons, doesn't matter. So it keeps on reducing. Okay, so recall the equation. So Wij equal to Wij old plus, it can be even minus, doesn't matter, delta W. But whereas that delta W is nothing but alpha times delta times X, right? So just recall, there is a delta coming into picture, right? So that delta is what we are saying, that it keeps on reducing as I move from the output backwards. If you have 10 neurons, right? So 10 hidden layers, sorry, 10, not 10 neurons, 10 hidden layers, input layer, 10 hidden layers, then output. You see, whatever delta you got here, it keeps on reducing. When you come to the first layer, maybe it is very small. But if you, instead of 10, if you have 100 neurons, then we face a bigger problem, right? This keeps on reducing, and after maybe 20 layers, it may reach back, right, from the output. 20 layers, fine, you have some value for delta. After that, it becomes so small that computer will not be able to hold that, because there is a restriction. What is the minimum number you can hold? 10 to the power minus something, some number. That's a very small number. If the value becomes much lesser than that, computer will take it as 0. So you see, the Wij is equal to Wij plus that delta W is there, right? That is 0. Correct? So no, it means in this particular iteration, the meaning is that you don't have to update to it, because delta W is 0. So what happens after that, right? From the output, I said 100 neurons, say 20 neurons, they get updated every time. But before that, I have 100 layers. Okay. So 20 layers are fine. Remaining 80 layers, they won't get updated at all. There is no learning at all. Correct? So though you do a lot of iteration, right? So this is what happened earlier, right? So people thought that, okay, I increase the number of layers. I don't see any change. Machine is not learning. People thought, okay, let's increase the iterations. What's the use of increasing the iteration when machine is not learning at all? Right? So very fundamentally, this is the problem. Simply, if we increase the number of hidden layers, right, the error which is propagating backwards will not reach your towards the input. It will not come closer to the input at all, right? So this problem is called as a vanishing gradient problem. All right. So similar points I have written here. So error is propagated backwards. That's fine, right? And error hardly reaches the first hidden layer. Final layer onwards, it comes back. Here is the first hidden layer. Before that, I have a input. So as of now, what we understood is that it will not reach. So when error is E, you are not able to calculate an E over there, which means if you don't have E, you don't have delta. You don't have delta, you don't have beta. So it's like, so they are related in this way. So the overall, the big picture is that the hidden layers which are closer to the input, they are not at all getting trained, right? So this is the final thing I mentioned, right? So when there is no training, right, when they're not getting updated, what's the use of training, right? So try to represent a, let's say that there are many hidden layers here, okay? So in this part, normally I calculate a error. It's a E, right? D minus Y. I have a delta value here. This delta comes to the first hidden layer as delta 1. We have a matrix. Delta 1 becomes delta 2, delta 3, delta 4, etc. If you have a huge number of layers, right, the last layer, which is the first hidden layer, will never get updated, or much before that also, it will never get updated. So that's what is happening if you simply keep on increasing the number of hidden layers. Okay, so what is the solution? We need to think of a solution, right? How do I make sure that the error propagates irrespective of the number of hidden layers? I want to pass the error, right? I want to pass the error. If there is an error corresponding to this, so there is a delta. So delta means there is an error. We'll call it as a E1. This E1 should propagate to the next one. I should be able to represent a E2. From the E2, I should be able to calculate a delta 2. This is the problem. So now you tell me, who is the one, who is the culprit over here in all this, in the whole scenario? Who is the one trying to reduce that error, and why the error is reducing when it is propagating from this to this is my question. Can anybody think about that? Yes, that's correct, Jyoti. So derivative of the activation function, if you remember the calculation of the delta value, right? How do you represent the delta value? It is the phi dash of some variable v or x, whatever, into, right, into your output, correct, into the delta value. So phi dash of v into delta, correct, into e minus a, not delta. Delta equal to phi dash of v into the error, correct. Now you see, what can anybody tell me what is the maximum value of this phi dash of v? You have to remember the, I think we have plotted, so mentioned that we need activation, we need activation function plus its derivative because of some reason, right? Now I'm coming to that. So what is the maximum and minimum value? If you remember, maximum value is 0.25. Perfect, right? It's a derivative. I'm going to show you the graph now itself, maybe in the next slide or next of time. Okay. So we understood that, right? The calculation needs the delta, not just delta, it's a derivative. Phi dash of v into error. Okay. Now that will give me a delta. That delta I'm going to use for the calculation of next error. In terms of that, I'll multiply by the phi dash once again, right? and I get next value. So you see, I'm whatever is the value of error right now I have, maybe the output layer, to that the best multiplication could be 0.25. In the sense, it's 25% will be considered for the previous year. Okay. Anyway, I got some value, no problem. From that delta, if you want to calculate the error previous to that, you get an error. From that error, you calculate the delta of that. Once again, you multiply maximum value is 0.25. That's the best thing you can do. Always we multiply lesser than 0.25. Now you see here itself, there is a lot of reduction from the first output layer to the first hidden layer itself is, this is 0.25. From there, the next one is again into 0.25, right? So phi dash of V into the error. Normally error may not be too large. Okay, so error is also less, the multiplication is also less, means you keep reducing the values. That's a mathematical view. What is happening, I'm going to show you. So yes, the answer is right. So who is the culprit? The activation function is the culprit. So what is the activation function you are using? Sigmoid. So now it's time to change the sigmoid function. So deep neural network overcame the issue of the vanishing gradient by simply changing the activation function. Yes, now people can guess that this is what we have been using so far. ReLU is the solution. How the ReLU solves? Yes, we'll come to that. Okay, so let's look at the mathematics behind this. Anyway, I'm not going to deal the mathematics for a longer time. Let's just look at an equation.
Yeah. So I have one question. So is there any fixed rule like in neural network, how many hidden layers we should apply? How many we should create?
Okay, I'll try to answer. Right. I think once we had some discussion about this, but anyway, it's fine for me. See, first thing, when we go for a deep neural network architecture, right, a lot of research has been already made, and there is something like a standard, what do you call, network is available. Trained network itself is mostly available. So that can be considered as the state of art design. Something like Google has done a lot of research and they have generated some network. Okay, so if my data set is something similar to them, it is not normally, this is what we follow. We directly start with a architecture which is similar to their structure, like 100 layers, because they may have, during the training they had 10,000 data sets, 10,000 for each of the class, and they may have 10 classes, 100 classes, etc. Okay, so what we do, first we look at the what research already has been done, and we'll try to assign something similar to that. May not be exactly that. So they may use 100 layers, you may go for start with this 50 layers, because I want to reduce, I don't have a computationally efficient hardware. Maybe I may not have a GPU with me. Okay, so I prefer starting with at least 50% of that value, and later on definitely I can increase. So like that. Again, second part comes from the practice, right? You already have done a project which is very similar to this. Initially, even I had no idea, right? How to start, from where to start. I even searched many textbooks, very standard textbooks, Simon Hacking, right? Many books we refer, but no fixed answer saying that, okay, this is the only, for this problem, these many layers. Second problem, these many layers. No, it is not. Okay, so first method which I mentioned, right? Refer some one who has done a similar job or some state of art technique, like, so those names I'm going to I think we'll be able to deal that in tomorrow's session, right? What are the specific pre-trained networks available, right? They are very standard, right, which you can refer, and what type of problems have been addressed by those, that also I'm going to give. I'm also going to show you their architecture. Okay, it has so many layers. First layer is this, next layer is this, it is connected to this using this activation, etc. That's also what we are going to see in the next session. But to answer your question, there is no fixed numbers written anyway, right? Again, depend, you got, let's say I am solving a problem, and in a classification problem I want to achieve an accuracy of 90, maybe 90%, 95%, which is somewhere considered as a good one. So after attaining that, then you have the freedom to change all the parameters. When you do that, definitely you will get a better result than what you are expecting. So that's a trial and error part. So just to reach the some standard values, you will always use something which is existing. You refer the papers, publications, or the standard networks I mentioned, right? So those things can be referred as a standard benchmark. On that, you can try your own, right? Slight modifications because they have done a lot of research to come to that level. So GoogleNet can classify 1,000 categories. 1,000 different images can be classified using that network, which means they have done a lot of training over there. Very optimistic weights have been identified, etc. Okay, but yes, you can start from some part of that. You can think that okay, my problem is something similar to that. I also have a huge data set. I also have a GPU with me, etc. If you think that, yes, you can start with there, keep modifying, and right, you can achieve the optimum values. All right. So, will that answer your question?
Yes.
Yeah.
Alright.
Sure. Any other doubt?
No.
Okay, all right. So now, just now we discussed about the vanishing gradient. I just try to explain, right, in words, what exactly is happening. Right now, let us try to consider the same situation in a mathematical way. All right. So I don't want to go in very depth about the mathematics because, right, we have an equation anyway. If I'm doing a 10,000 iteration, there is no meaning in doing the manual calculation. So I'm not going to that level where we substitute a value and simplify. It's not required at all because we'll never do that calculation in the whole lifetime, right? Simply call a function, it will do the job. But just to understand the mathematics behind that, let us consider the back propagation algorithm with, say, 4 neurons. Okay, first neuron x, whatever you see here as x, right? So this x is the input. So anyway, that has nothing to do with that. The last one you see is an output. That also you don't have to. It's an output. Fine. So in between, right? In between the input and output, I have 2 neurons. Right? Only 2 have been considered again for simplicity. My intention is to show you, right, the equation. Since I have only 1 neuron, I don't have to look at the connections, etc. Right? That's the reason. So 2 hidden layers. Each layer has one neuron. All right. So Z1 is the partial output of a layer, and after activation, I get a W2. I get a F1. Gets multiplied by W2 as a weight. Partial output Z2 is created, right? Again, apply activation function F to get an output. All right. So this is the whole structure which we are considering. Now, let's try to write a weight operation equation for W1. So W1 is equal to W1. So it can be plus or minus, doesn't matter because, right, depending upon what loss you calculate, it will be, right, accordingly it will change. So plus or minus, right, eta times delta value into the loss, right? Fine. Now, this part, right, is the derivative, right? How much loss occurred because of wrong calculation of W1 in the previous case. This is the fraction I was talking. In my output value, how much error has been contributed by a particular weight. That's what is the change in the weight which we are calculating. So one of them will calculate. So that is this equation, right? Out of that loss is simply subtraction for us, d minus 1. Out of that loss, how much came because of this? So it's a partial derivative. So if you remember the mathematics, right? So partial derivative is one very important aspect that needs to be applied several times if you want to look at the mathematics behind each and everything that we are going to study in machine learning and deep learning. All right. So everywhere it's a partial derivative plus the chain rule. Okay. I'm coming to the chain rule next. Right. So this can be simply calculated as, right? I don't know the direct calculation because W1 is here. The actual loss occurs over here. Whatever loss we write, right, that is D minus 1. So we may not be able to directly calculate that. So what we do, we'll expand something like it is partial derivative dou Z1. Z1 is related. You see, Z1 is happening in that node itself. Right? So I can try to write. I can split that term, dou loss by dou W1 as how much Z1 changes because of change in the delta. Delta W is a small change in the weight because weight was, right, not properly changed, right, in the previous equation. Because of that, I have a small change. Corresponding to that, I have a change in my present output, in the sense output of that particular layer. And I can actually, right, using the right chain rule, I can actually write it in this way. It's actually one and same. If you look mathematically, these two are cancelling. I still have right dou loss by dou w. Right, I can do this. Right. So this part is what we will call as delta. I'm doing the from the input side, I'm going to the output, but I'm trying to give what we had calculated earlier, delta 1, delta 2, delta 3. They are what, right? They represent which particular feature physically I'm trying to answer that. All right. So this is what we have. Fine. Now let us go further. You see, I had, right? I can actually extend this further, keep for extending further. I have F1 over there because after the activation function, I have a term coming, right? So I can actually bring that into picture. So dou F, now you see, I have this loss by Z1, dou loss by dou Z1. I'll try to explain that itself. I'll try to represent that by using or by expanding this using the same rule once again. Okay, so this is nothing but dou F1 by dou Z1. Okay, F1 actually, right, in F1, changes in F1 definitely will result in changes in Z2. Okay, because F1 into the weight 2 gives you Z2. So I have to bring the right that also into picture. So this is dou Z2 by dou F1. Ultimately, you see this cancels. I still have dou loss. Dou Z2 is also cancelling, right? Ultimately, mathematically, I see it's still the same. I'm calculating the same. This is what we call as a Z delta, right? This delta 2 can be written like this using delta 3. Only this delta 3 can be x, right? Till you can split like this. Now, since we are considering only 4, maybe we'll stop there, but this is how it propagates. Now, the point which we mentioned earlier should be very clear to you. That is, I can see that this delta 4, right, has actually, you see the derivatives coming into picture, right? So many derivatives are being used, right? Out of them, many of the terms are because of the derivative of the activation function, right? So that activation function's derivative is maximum value 0.25. Right? So I may multiply 4 times here, 0.25 power 4, very small. Into the other terms, which are also smaller, you get a very small value. So maybe you get a value here, maybe you get a value here. You may not get a value here, right? Because of this kind of calculation. So again, this is just 4 neurons connected one after the other, out of which 2 are the hidden layers. I just wanted you to show you, okay, this is what is ultimately going to happen. Since if again, if you are not changing your activation function, you still keep the sigmoid, yes, there will be serious issues. Okay, for that reason, in the neural network, right, coming when we jumped from the neural network into the deep learning side, and by changing the neural network architecture, the first thing to be done is changing the activation function of the layers other than the output. Okay, so we change it now. So I'll just come to that point. Quickly see this. So this is the same graph which we had plotted in one of our previous classes. So this, the blue color, what you see is the f of x, that is the sigmoid function. Sigmoid function takes a value 0 to 1. But when you differentiate, whatever you get is this curve. You see the highest value comes closer to 0.25. Okay, so that's the highest value. So again, you multiply by that value only if your value is 0, right? Normally we don't have 0. There is some other value coming, right? If this comes, you multiply by a much smaller value. If value is minus something, you multiply by a value closer to 0, right? So because of that, we have the serious issue, and that's what we are trying to address now, and that is called as the issue is called as vanishing gradient. And yes, so we know the solution now. We'll move on to the solution, right? Before that, yeah, so the same point I have mentioned. Okay, sigmoid maximum is 0.25. So product of the derivatives, right, will become negligible value, close to 0. So whole concept is called as vanishing gradient. So the solution, already we have plotted, right? So I'm not going to show you that again now. So it's a ReLU function. ReLU will compare any input with the 0. Whichever is maximum, that will be passed. Okay. So on the right side, more than 0, it is a straight line. Okay. It's y equal to x line, right, on the right side. On the left hand side, it is completely 0. So line will be until 0 from the all the negative values, it will be 0. As soon as this crosses, it becomes this. Okay. So now, can anybody tell me how this ReLU function solves the vanishing gradient problem? Okay, you can answer orally or you can type. All right. Right. ReLU activation function we know, right? So anyway, it has to be related to the derivative, because over there also, even if you use change over activation function, ultimately, right, we are expecting something with respect to the derivative, right? Because derivative should not be smaller. That's what we are expecting. Okay, try to relate that concept and try to answer.
So this derivative of ReLU is 1, maximum value is 1 for all the positive values.
Yeah.
So each time when we are back propagating, we are just transferring the error only,
yes,
because derivative is 1.
correct, perfect. So what happens, irrespective of whatever is a error value, okay, doesn't matter, take a derivative. If the value was greater than 1, it always becomes derivative of number which is greater than 1 is 1. So always the delta value you calculate is 1. Sorry, the phi dash of whatever you calculate is 1. So it is not going to change. It will never reduce. Whatever it has come from the previous layer, multiply that by 1, pass it to the previous layer. Okay, so that means I'm not reducing. There is no 0.25 getting multiplied. You multiplying by 1 or 0. There is a possibility of 0 because negative values will be truncated to 0. Right? So no negative values concept at all. Okay. So because of that, now it should be very clear that yes, right, by just changing the activation function, actually the sigmoid was complicated. Now we actually, right, came to a function which is very simple, right? Negative, it's a 0 on the complete left side and it's y equal to x on the right side. Whatever you give as input, it will be passed. So that is activation function. Plus derivative is 1, right? Fantastic. So now we have the solution to this. That's the significance of ReLU function in case of a deep neural network, convolutional neural network, or any type of the deep learning related neural network, which has a large number of what you call a large number of hidden layers compared to the simple neural network. Still, it works very efficiently because of solving all these problems. So this was the major something like upgrade, right, that actually happened, right, inside the concepts of deep learning compared to the simple neural network. That's why there is a bifurcation. So simple neural networks are considered as a part of machine learning algorithm. They will learn some, but there are deep learning, right, on the other hand, they require a lot of computations. Okay, they're only if you have a GPU, yes, fantastic. Otherwise, it's going to take time for training, etc. But they will give you a good result. Accuracy is right compared to the machine learning techniques. We expect a much better accuracy when we go for a deep learning. But on the other side, if there are some upgradations compared to the simple neural network to this. Okay, so any doubt with whatever we were discussing so far?
Excuse me, sir. Sir,
Yes,
if we will use this tangent hyperbolic, then this gradient vanishing, it will occur there or not?
yeah, it will occur. It
The
will,
max.
it will. Yes. In
Okay.
all the other activation functions, we have that problem because the derivative is much smaller than than 1. So as a result of that, it will keep on reducing.
Okay, sir.
Right? So other than ReLU, anything we know so far, right? If we apply that, there will be problem. Okay, so only thing is we can do is we can upgrade from ReLU. Do you have any upgradation? Yes, answer is there. We'll come to that right at a later stage, not now. Okay, so far we try to solve the various problems associated with the simple neural network when we try to increase the number of layers or number of classes, etc. So you see, we started from very simple case, then we came step by step. All right, so now we are entering into the deep layer. So we have, right, many concepts around us which we actually derived from very scratch. All right. Okay. Any other question? Okay, then let's move further. The second problem, again, we are going to see this when we simply increase the number of hidden layers. Or it's not just that, even our deep learning, we have this problem because deep learning has a lot of hidden layers. So what's the fundamental problem, right? Fundamental problem is, the term is overfitting. I'll come to the overfitting. I'll come to that later. Right? So let's try to see the problem over here. When we have huge number of weights, doesn't matter you are using a neural network with large number of hidden layers or a proper deep learning based thing or a deep neural network, doesn't matter which one you are using. We will face a problem called overfitting, right? Overfitting is defined in this case. You see this kind of graph we get whenever I try to perform I try to do a performance analysis. What do you expect? Normally this is the ideal case. Complexity, in the sense, maybe you can say that number of hidden layers are, ultimately speaking, the number of hidden layers increased means number of weights are much more than maybe 10-fold, 100-folds of whatever layers you have, because so many connections will come. So when the training happens, I am supposed to update each and every weight that is present over there, right? That's the simplest way to understand the complexity. Complexity in the sense, how many number of weight updations you are supposed to do, right? Further subdividing that into the computer's algorithm way of answering to that point, it's number of additions, multiplications you do for the weight updation. So as the complexity increases, all these things will come into picture. I need to do more and more weight update, do more and more multiplication, addition, etc. So complexity increases. So when I'm doing so much, when I'm going to put so much of effort in the training part, what do you expect? As the complexity increases, the error should decrease, right? Error in the sense, the chance of making a wrong decision, that should reduce, right? But this is what happens. You see, now you consider this particular graph. So, right, we are plotting the complexity over here, and the error is plotted over here. So, because of overfitting, again, overfitting happens only because of large number of hidden layers, large number of neurons in the hidden layer, which resulted in the large number of weights to be updated. Because of that, this is the common problem. You go for a deep learning neural network, everywhere we have this. So it keeps on, error reduces. Still here we are fine. See, till this, it's a best fit. Till there we are fine, right? Till there means there is a specific value of complexity, right? I go beyond that. I feel that, okay, let me further increase the complexity. Let me add few more hidden layers, right? And I'm going to expect, okay, my results will further improve, right? I will get lesser and lesser error, but unfortunately that's not going to happen. You see, after that, error increases, wrong decisions will take place. That's why the error increases, right? This is happening not in the training part. You see, training looks very fun because nowadays, if you have observed any tool, right? Maybe the Python also has an option to just to visualize, right? What is the error that occurred during the training? What's the error that we are going to we get in the testing? We can visualize separately. We can plot, or simply we can actually just to display over. We can do that, right? Or even the other tools like MATLAB will have a specific window over there. Whenever you train, it shows, right? Validate, it shows. Testing also it shows, like it gives you a display plus it will plot something. You have options in almost every tool, right? What happens? Training shows very fun. You see that this is what is expected, right? The training was still here. I was not satisfied. I increased the complexity. Training went ahead, and your results are fantastic. Yes, it says that, okay, training the error is minimum. Okay, that's fine. But during the testing phase, right, the actual picture comes into picture. The actual picture we can see, right? So it comes to a minimum up for some time. After that, error increases. So there is, right, no effect of increasing the complexity beyond a particular setting level. All right. So this problem is what we call as overfitting, right? We say that machine learned more, much more than required. So it started answering randomly, wrong answer, right? So again, the point is directly related to the weight, right? Number of weights are too much, right? Maybe computational load which the hardware took, right, to train them, right, has no effect on the recognition part or on the testing part. So testing error shows a right, completely different uh, uh, whatever yeah, sorry, the testing curve is going to be completely different compared to the training error. So basically, error increases after a certain level of complexity. So this problem is what is called as overfitting, right? So in terms of error, this is the graph. Okay, if you are look at the accuracy, this is the curve. It's a reverse, right? So, right, when the error increases, accuracy should decrease. So you may see this second graph also in some of the references whenever you refer. So don't get confused. It's one and same. So instead of plotting the error, you may plot the accuracy versus the complexity, right? So again, the complexity is in terms of number of epochs, right, which you use to train. That's also fine, right? So you may think that okay, number of epochs, whatever I train may not be sufficient, so I'll increase that. So 10,000 to even you go to 10 lakh, no effect at all, right? So that's because of this kind of representation. So again, you see the very peculiar nature. The training shows ultimate result. Training says that yes, I learned everything. But when a question is asked, right? Okay, classify this and tell me. You say that it's going to come down. So this part is what is the result of. We call that as a technical term overfitting. Okay, so fundamentally, this is the problem. All right, so do you have any question related to what is overfitting? Okay, please ask. Then we'll go for the solution. How do we solve this? Any question?
So how we will distinguish between overfitting and underfitting during test data errors?
So it's something like normally this is the procedure. Whenever we don't go for something like too much number of hyperparameter tuning. Like minimum is there. Again, I told one answer in the previous question, right? So how do you define how many number of layers required, etc.? It matters, right? So I should not go for something much beyond that. So somebody already has done a research and they have given that okay, for me this problem worked with 500 hidden layers. So I can try close to that, like 450, 600, 700 should be fine. Don't go beyond 10,000, 1,500 will work according to me, not an issue. But don't go much beyond that. That is going to result in the overfit, right? So somewhere around you can do a trial and error, and you will get a best suitable results for the given problem. Okay.
So do we need to do research before modeling every problem or issue?
If it's a similar problem to the one which you already have solved, you may not have to do a lot of research. But when you're starting with a very new problem, right, it is suggested that you read some references who have done similar problems and what was their approach, how many, because you need to decide the hidden layers, right? It's not suggested to start from 10, 20, keep increasing and so on. That's not suggested. At least start from the one which is closer to the one which is already there, right? So normally if you consider some very standard networks, right, so they are able to solve, right, most of the problems. Means you can start with something closer to them, or you can actually directly bring them, you can directly use them itself in your problem. You have options, right? But suggested to start with something closer to those values. All right.
Okay.
Like that that's the common approach, because deep learning, in the sense, there is a lot of things to learn for a machine. So instead of making it to learn from very basic, like starting from 10 layers, 20, then increasing, that actually is something like it's like it can be considered as waste of time, waste of the computational resources, etc. Because already somebody has done that and they came to this point saying that okay, this problem can be solved with using 500 layers, etc. Right? So better to start from there. Okay, that's the ideal scenario as of now. All right. So any
So
yes.
one like okay, in a basically in a normal like okay supervised unsupervised learning in a basic models we used to use grid search or a CV. Is
Okay.
there a similar to that where we can like okay use a elbow method to really determine like okay these are the right hyper parameters for deep learning models?
Okay. Yeah, we have a technique that actually in which again that will be coming at the advanced keras part. Okay, it's there, right? But anyway, we may not touch that part, but since you raise a question, I'll try answer that question. Okay, so it's something like we have a specific feature which actually you can actually provide the range of the hyperparameters which you want to test with because I don't have any idea that okay, this is the optimum value of the hyperparameter. Maybe it can be weight, number of hidden layers, etc. Many things, right? So I'm not very sure, right? But I have a facility to provide an input saying that okay, vary this particular parameter from 10 to 100. I'll give another like that. You can actually specify when you write a code, right? The machine runs for each and every values. Okay, each it's like for loop so many times because if I give say one of the parameter from 10 to 100, another parameter maybe I don't know what is the ideal learning rate for my problem. All right. In that case, what I do, I'll give a range for that also. Start from 0.01, go till 0.9 maybe. Right. It will run for that also. For each case of my previously mentioned hyperparameter, this will also be considered in a complete range. In that, it will be considering another. If you mention any other parameter, it will consider that also, right? Completely, it will take care of each and every value. For each and every value of the hyperparameter, it will provide you your metric. Like if you are looking at the accuracy, it will show the accuracy. You want to look at the F1 score, you want to look at the true positive, true negative, etc. Whatever, right? So every value will be calculated and plotted over there. That will be a huge what you call result. It's there. And out of that, which is the best one also, you can ask the machine to tell. Minimum, you may want to reduce the time, right? It will actually every time it will calculate many more things as well, many more parameters like the time consumption, the complexity, how many times a loop is actually going to iterate, etc. will also be considered. If you want to go for the best one, you have a freedom to ask the machine, suggest me the best one. It will tell that okay, if you use alpha equal to this, number of hidden layers equal to this, and other parameters like this is the right. This is under these conditions. These are the best possible hyperparameters for your problem. But the program will run for 5-6 days and so on because for each and every value it has to do the training, right? If you have a 10,000 data set into two sets like 20,000, it should go so many times, right? So if time is not a problem but I want a ultimate result, I prefer that, right? So right, if we don't have any idea about that, that is also preferred, right? That can be used, but anyway, you have to invest time over there. Okay, so that method is there, right? Something similar to the grid search what you mentioned.
Thank you.
Okay, yes, sure. Is there any other doubt? Okay, so now is the time to solve this problem, right? So what do you suggest? So the problem is pretty straightforward. I have huge number of ways to update. Maybe every iteration I have a huge data set, sorry, huge number of ways to update. That's my major problem. So what is the solution that you can think of? All right, yeah, you please think about this and maybe please take 1 minute of time. So the problem is that itself, I'll repeat, I have huge number of weights to be updated. So the only solution is you reduce the weights. How do you do that? So we have so many number of connections, right? So every connection will have a weight. So if you say you remove the weight, it means there is no connection, correct? So you cannot make weight as 0, right? Okay, that's actually what everybody is going to think, and that's correct as well. But people have done some research. What happens if I leave some weights, right? So that actually gave a wonderful result. So that's what we are going to discuss about that now. So now I gave you hints. Okay, so please think about that, and right, whatever you think, you please give me an answer. Okay, doesn't matter, because people came to know this only after doing some research. So I cannot expect you to give me the right answer on this, right? So please think about that. How do you reduce the number of weights uh, for an iteration?
Similar to something like, okay, batch or a mini batch update, or something like, okay, dropping out, or skipping some updates.
Yes, perfect. Okay, so that's the answer, right? We have a technique called as a dropout. All right, so we go to that. All right, so you can see here, right? So the technical term is called as a dropout. Okay? It's called as a dropout. What do we do whenever we have such a huge weights to be updated? We use a technique. We use this technique, dropout, right? Say dropout in the sense I have to choose a smaller number, somewhere around 20%, 30%. It's like a 0.2, 0.3, something, representing a percentage, 20%, 30%. So for a given particular layer, when I say dropout of 20% or dropout equal to 0.2 when I write a code in TensorFlow, Keras, or what it suggests that you randomly leave 20% of the weights during the updation. Don't do any calculation. Keep them as it is in the previous case. So it has to be done not the same weights in the next iteration. In the sense, iteration wise, you should change these 20%. Right? I have 10, let's say I have 5 connections over here. So 20% I'm supposed to leave. So I leave this one for the current iteration. Update, I will update the remaining 4. Next iteration, randomly I will cancel another one, update this. So next, at randomly cancel any one, right, do this. So this is what people have done in research. Is there any problem? They found that no problem at all, because you have such a huge data set to train. You have 10,000, right? In one iteration, one of the weight you miss, no problem. This 20% may look smaller when I give an example of just 5 connections. But when you go for a huge number of connections, this 20% of less burden of calculation means a lot. Okay, so again, this is, we cannot mathematically prove by doing a derivation saying that yes, this is efficient. No, this is research work. They have done a lot of research on this, and again I will give you a range. What range is normally used for dropout? 20% worked fine for me when I did some projects. Okay, but definitely yes, you have a range defined here. Again, that has been taken from various research works, right? Within that range, if you use, right, there is no effect. It will not bring your performance down at all. It will keep it same, whatever you used to get earlier, the same thing, but with the less number of computational load, right? So you see here, this is one example what you see here. So maybe some dropout has been chosen. So in the first iteration, maybe this is iteration number nth iteration, this neuron has not been used for the weight updation. You see, weights of these neuron, this particular neuron has not been updated. But you see the next iteration, below that you can see that the last one they are going to leave. This is not used, these two are updated. Same thing happens with the next hidden layer as well. You see here. In this, again, it looks like 50% drop has been used. It works. 50, 55 is also going to work. No issue. Okay, when you have very large number of neurons, okay, when you have less number of neurons, don't go for these concepts. We don't require dropout, and we don't have even overfitting. So whenever you feel that okay, we are getting a overfit problem, this is the solution. So here you can see that, right, the first and the third were not present, In the next case, you can see the first and third are present. The second and the fourth neurons are not considered for the rate upgrade. So you drop off. Okay, so and we have right various ranges provided right for hidden and input layer. Even the input layer it works. Okay, you can definitely apply right whenever I have a huge image data set, right, you can neglect some of the inputs because those pixels, right, because I have 1000 into 1000 pixels. If you leave 200 pixels, that may not cause any major issue. Okay, so that was the second upgrade, right, that we can see when we move from a simple neural network to the deep learning based neural networks or deep. All right, so any doubt with the solution that we discussed, that is the dropout?
So no doubt about the solution, but like okay, it came in one of the lecture you mentioned about the like okay, when you are using a neural network, the people expect the highest accuracy or a prediction.
Okay.
So what is like okay, when we can say like okay, what should be the accuracy for our model that could be accepted by most of the people? For example, in certain in a normal, not a deep we
Okay.
say that okay, above 70, 75 or 85, 96, it's excellent. So in case of a deep neural network, is there like okay, people say you have to have like okay, acceptable neural net. Basically, it's a network, whatever is it. If it's above 95 or above 90, it's a like okay, acceptable solution. What is that?
Ideally, I can say, I can answer that question. Something like if the data set is proper, there is always a condition. I always, whenever I get a new project, I will check. My first question will be, what is your data set? So if the data set is proper, then the next parts will come. Because as I told, if the data set is maybe if it is a sensor based data, sensor error comes into picture, right? Because two or more data sets may look similar, right? That's one problem. If you are collecting the data set from some different source and source did not collect it properly, and mixture of data, class A data is present in class B in class B, and when you have like lakhs of data, you cannot check each and every one manually. So that's why I told, if the data set is proper, right, normally 90 plus will definitely achieve in the deep learning. Okay, 90 will definitely cross. Okay, so 95 and up is what normally people expect, right? So okay, you are using deep learning, you are using so much of what you call computational effort you are taking. Your machine, you have the GPU, you apply the complete with the full power, you are operating on a GPU to train for say 2 days, and then you say that my accuracy is 60%. That's of no use. You get the same accuracy with others which will run within 10 minutes, right? So that's what I'm saying. So when you do a lot of computation like that, so 90 plus is the normal one. Most of the algorithms will definitely achieve, provided data set is correct. Okay, so if we don't have, again in my practice, in my past experience, I have seen, right, good code, right, very efficient hardware, etc., still giving 80%, 80 to 85. So then we understood that okay, then we tried to explore that further. Then we understood that okay, there is some issue with the data set, right? So once we rectified it, it crossed 95 later. So that's what. So 90 will, you can achieve easily 90%, right? And 95 plus is people expect normally. When you say that, you are using a deep learning.
Okay, thank you.
All right. Then that was the second issue that has been resolved when we move to the deep learning. And then we move on to the next one, that is the handling of the computational load. So this problem was there, right, whenever we were using other machine learning algorithms as well. So even we have the ML algorithms which run for a longer duration. Okay, but when we come to the deep learning based concepts, right, the first thing, right, we have the neural network based concepts were extended further by bringing some concepts such as the CNN. We understood with the diagrams, we had understood what is the problem when it comes to the CNN, when it comes to the normal network, and when it comes how it gets solved when we go to the CNN. I think the example was identifying a specific object in a specific location. Neural network will identify only if it is here or here, because we trained over only here. If the object is somewhere here, it will not identify. So those problems are solved by bringing the newer algorithms or newer approaches, right? Like the CNN. So algorithms are different. That's the first thing. Second thing, whenever we change algorithm, we understood that we need a lot of computations, because definitely you have more layers, right? In order to learn more and more new features, we understood that we needed to extend the we call we had to extend the layers. So means more computation. Say that itself is a computational load. So how the computational load or whatever burden we have, right, will be maintained by the deep learning related concepts is by the usage of efficient hardware. So they are capable of utilizing the GPUs present in your system. So again, it's supported by the other libraries, etc. We have to use it. But if there is a facility, you can, like TensorFlow. Normally, we suggest the students to install the TensorFlow normally. But when you have a GPU, you have an option to use the TensorFlow GPU library, which actually runs on the GPU if you have it on your system. Okay, same thing. Keras. We say that okay, install Keras and run the fine, absolutely fine, no issues, right? But if you have a GPU, always you should go for TensorFlow GPU. It's a different version of the same thing, same Keras or same TensorFlow, but efficiently built, optimized for utilization of the extra memory or extra graphics available in your system. All right, so that's what that is available, right? So because of, though it were available earlier, or either the cost was too huge, people couldn't afford, but nowadays, right? So we have the graphics cards, plus we have the deep learning methodologies available. Various networks are already either pre-built, or you can use anyone's network which already has been trained on your system, and you can train some, you can make modifications and train on your system, right, etc. Those can be, that is possible now. So because of that, the computational load which is there in when we try to solve any issue, any problem uh, in the based on the deep learning techniques, right, it's easier. So the computational load whichever is there, right, it's not like a big load now, right? Even we have the parallel pool available, some of the tools available parallel. I connect 4 computers and the problem gets divided into 4 pieces. 4 different processes will, right, so do it parallelly, and finally you get a result. Parallel pool is available, etc. So because of that, the computational load, right, which look like a huge task for maintaining or balancing when we use the other ML or simple neural network, right, that is not there right now. Okay, so again, a lot of research has been done on this, and then only this is the result what we have now. Again, result is being, sorry, research is being extended still now, also it's going on, right? And maybe we get much faster GPUs are replaced by TPUs in Google's Google terms. They are processing the tensor processing units. So anyway, more things will come in soon future, and maybe this load will reduce by a huge factor in soon future. Okay, so those are the 3 major issues addressed by shifting to the concepts of deep learning. Okay, so do we have any doubts with any of the topics we have discussed so far today?
Sir, actually, no doubt about the points we discuss or the topics we discuss.
Okay.
But this is something like, okay, I may be jumping towards little bit. So now we have like, okay, a big, suppose we are implementing image, basically identifying image identification for maybe 10 or 20 types of images, classified images.
Okay.
So when we train it, after training, we need to like, okay, deploy it. So is there a different way to deploy it, or do we need to like even like okay have this training set to be like okay made available during the actual use of that?
No, no, no. I'll answer. I understood the question. So
Yeah.
training happens only once. Okay, training will happen only once. It may take 2 days, 3 days, 5 days, 10 days, etc., depending on the complex. Okay, once it gets trained, right, you get a trained model. All right, so the trained model is the one which you need to save whenever you want to deploy. When you want to deploy somewhere, you will use only that trained model. Trained model will have what are the weights from where to where. These are the optimized weights. I need only that. Okay. Then when you actually deploy, what you do, you will test. Right? I'll give a unknown image to this machine. Machine has been trained in the sense I have a variable which holds all the values of weights, biases, or anything, which are the hyperparameters of that particular machine. So when you test, you simply pass on a new image to that. It will simply tell you a no. That's all. So testing part is pretty simple. Only the training part, which actually is computationally like there is a lot of computation load, etc., is there. That has to be done only once. Okay, simple. You do it somewhere. Use a GPU, TPU, whatever you have. You do it. You save that in a variable. Use that variable whenever you want to deploy. Okay.
Yeah, it's a similar to like okay or the ML model deployment.
Yes. ML model deployment. Same. Very simple.
Yeah.
Okay.
Yeah.
There'll be not much difference. Very simple.
Yeah, thank you.
Okay, all right. So do we have any other doubts or any other topics to be discussed now? Okay, so that brings us to the end of today's session. I hope this session is useful to you. We will be considering more and more advanced topics in the coming session. And we'll meet tomorrow, same time. Okay, all right. So
Thank you, sir.
Thank you, sir.
thank you so much. Thank you for your patience.